Professor Pan received his PhD degree in solid-state physics from Saarland University in Germany. After his postdoc research at the Max Planck Institute for Metal Research in Stuttgart, he joined the Faculty of Physics, Department of Material Science and Engineering at the University of Michigan in 1996. He was appointed as honor professor and the director of the electron microscopy analysis laboratory at Michigan. He then moved to the University of California at Irvine in 2014. And he is currently a professor and Henry Mueller Annual Chair in Engineering in Department of Chemical Engineering and Material Science and the Department of Physics and Astronomy. He's also the director of the Urban Materials Research Institute. Professor Pan's research focus including the understanding of the atomic scale structure property relationships of advanced functional materials, including oxide ceramic electronics, ferroelectronics, and multi-ferronics and catalysis. He's recognized internationally for his work in electron microscopy, and that has led to the discovery of new properties and novel functionalities in this technologically important materials. Professor Pan received a number of awards. This long list, I just pick up some, like the award of American U.S. National Science Foundation, the Outstanding Young Investigator Award of the Chinese National Science Foundation. He was an overseas member of the Scientific Review Board of the Chinese Academy of Science in 2005 to 2010, and he has been serving as a member of Advisory Committee of the Overseas Chinese Affairs Office of the State Council of China since 2011. He was elected as the Fellow of American Ceramic Society, American Physics Society, and the Microscopy Society of America. He has published over 200 peer-reviewed papers, including the journals in Science, Nature, PLL, Advanced Material, and so on. So today, he's going to talk about in-situ microscopy with atomic resolution at atmosphere pressure. So welcome, Professor Pan.
Thank you, Professor Wang, for very nice words for introduction. And also, I would like to thank both department and Institute for Advanced Study invitation and arrangement. I understand this is close to the end of the year. I already finished them. And thank you for coming to my talk. And I prepared the abstract a few weeks ago, and then try to have a focus talk. And then through the last few days interaction, I understand the audience even is small, but will be very diverse. And then I decided to broaden the topic a little bit. Probably will not go to the any depth of the individual topic too much. Then give everyone who comes a little bit and the microscopy. So in the end, so my talk will be focused on the application of electron microscopy in materials. First, I want to tell you a little bit about where is Irvine, and people always ask me why you moved from Michigan to Irvine. I just started. Real start was from this summer. I moved early last year, but transition moving from Michigan and Irvine. So you see Irvine is whole campus just looks like this, and it's built around the park. And engineering is in this area, and physical science in that area. Basically, my appointment is split through 2 different departments, and also try to establish a new institute called Irvine Material Research Institute. It is a university-wide program. And so you see Irvine is just southeast of Los Angeles. And around Irvine, there are several schools. Some of them is bigger than Irvine. You have UC San Diego, UCLA, USC, Caltech, Riverside, and many other smaller universities. So some of them have a very large material research program. However, including Santa Barbara, which is still further south, north of LA, they do not have a good material characterization facility. That's also to my surprise. Like Santa Barbara is very nice and with a big material research laboratory, also with a long history. However, they do not have operation-corrected TM. And Professor Wang has the state-of-art operation-corrected TM and installation and will be operation soon. But in Southern California, they don't have this facility until Irvine campus decide to commit about $20 million to establish a material research characterization facility and establish institute. So they tried to recruit me about 10 years ago, and my family didn't like to move. And then about 2.5 years ago, they said, oh, we get a big initiative and you're interested. I said, no. But somehow I helped them to plan the institute in the end, so I convinced them to join the university last year. So through this effort, initiative, and we set up following facility. So this is actually is a state-of-art surface characterization facility. It's a latest version of the surface analyzer from Kratos company called Supra. This was the first one in North America, and which has a lot of analyzer spectrometer and also have in-situ characterization tools, plus ex-situ glove box that can treat samples and also ex-situ and then put it back to the chamber and for the surface analysis. In addition to that, we also purchased several big instruments, especially electron microscopy facility. One of them is the very unique state-of-art scanning transmission electron microscope. And this just to show the spectrometer. The whole microscope is much bigger than this. And this is the first dedicated STEM with high spatial resolution and ultra-high energy resolution. I'll mention this in another slide. And the JEWEL most advanced ground arm, this 300 kV atomic resolution microscope with a specially built wide pole piece gap so that you can do a lot of in-situ study even with your customized holder. That is a cryo-TM for structural biologists, and the atomic resolution up 2 angstrom to 2.5 angstrom resolution structural analysis of biosamples. And we also have an in-situ direct electron camera that will allow you to record the dynamic change in the microscope. You can recording up to 1,600 frames per second. Each frame will be high-resolution image, not like a blowing individual frame in the regular video. So, and then we have a workhorse 200 kV transmission electron microscope and also STEM, and have a new FIP. So this was one of the initiative launched by Irvine recently. And then we have a new building, which never been used before, only 4 years old. And then have to do a lot of reconstruction. You know, they put microscope there, is require a lot of renovation for the field, vibration, and acoustic noise, and so on. We just take off all the original slab and then put a new slab, it's about 3 feet. And then have do the shielding for the electromagnetic field, both of AC and DC. The most difficult is DC. The field have to be smaller than 0.01 milligauss. About one order of magnitude smaller than the field. You see, the layer, the shielding has to be very it's very complicated. So this is, I think at this moment they are putting the last layer, which is a mu metal. And so this is the structure of the shielding. So first have a single layer of steel, soft iron. So that is good for DC and AC, but not to the standard for the dedicated stem. And then we have a one layer, quarter-inch aluminum, which is good for AC, eddy effect, perfect for AC. And then we have to further shielding the near DC. For example, elevator is moving, and even something, a big body, even few people work together around the room, outside the room, you will see some small change. So then the near DC have to be shielded with a special material, with new metals, the high permittivity material. So 4 layers, 2 layers, and then with spacer and another 2 layers. To make this shielding very expensive. Actually, just one room will cost about $1.2 million just for the US dollars. So this, after that renovation, so many of the microscopy room just looks like this. And then the installation of the microscope and start from last summer and then going to finish by end of next month. So this is a room for the dedicated stem. This instrument is really a troublemaker, and they require very low field and low vibration. That costs huge amount of money for just vibration of this room. So this is just a piece of a so-called -K table, which further attenuates vibration so that the vibration will be smaller than 1 micron for about 60 minutes. Somehow like that. So it's a huge commitment for the renovation. So the renovation project started with a bidding, and then only 2 companies like to bid. In the end, only 1 will be able to do it. And they were very nervous, therefore they asked like a safety policy and just ask much more than it may cost. And eventually, if they cannot do it, they have to probably pay back something. But anyways, in the end, they did a very good job. So this is the requirement criteria. You see that the field has to be smaller than 0.01 milligauss. But what they measure is 0.004. It's really work very well project. So this is the most recent picture of the installation of the FIP. And this is a cryo-TM, it's a workhorse TM. And the ground arm is still in the under installation and will be covered with a box after everything is done. And this is your engineer who is a developer of this microscope and installation. This is the data and doing the installation. It looks very, very attractive. In addition to those TM facility, so we have a variety of TM holders. The TM holder is also critical. You have microscope, but you need to have something to do the sample inside so that it can study structure, composition, electronic property, and so on. So we have a nanofactory holder. You can do electrical wire thing, and also technically you can also do the scanning tunneling microscopy in combination with TM. You can also combine with light, with electrical, and with imaging. And also the mechanical property can be tested in the real time structure and analysis. And for those people who are interested in the electrochemistry, like a battery, catalyst, or other reactions in the different kind of atmosphere, you can use either the electrochemical holder, or the very interesting one is the one developed by protochips, or the atmosphere pressure TM. Initially, my talk was focused on this. Still show several examples of study. Also, we have a variety of other kind of holders, do 3D tomography, structurally or compositionally. And there's many different kind of customized holders that people develop. But if you know the work, and then you can design holder and particularly the work you are do. So with such kind of microscopy facility, together with Gaten's direct electron detector, so-called IAS camera. One camera will also cost about $800,000 US. With a service warranty, is always more than $1 million. That's why the manufacturer of TEM complains today. Gaten is a company who making components for TEM, so they charge more than microscope itself. Yeah, you know this. So with such kind of a microscopy facility with different kind of holders, you can study many different kind of properties in different kind of environment or and different kind of forces. This is just an example. So from my work on the ferroelectric material, you can switch the ferroelectric domains and with a polarization flip back and forth, and just memory device, you can switch the state 1 and 0 back and forth. Okay, so ferroelectric material is characterized by its polarization. The polarization is the ordering of the dipole moment. Okay, if the dipole moment is ordered, and then you have a spontaneous polarization. And then spontaneous polarization can be switched back and forth between states. And so if this switching is possible, then this material is called ferroelectric, otherwise just a polar material. So for ferroelectrics, if you apply electric field, and then the polarization can be switched back and forth. This is the property that is used to build memory devices. So to study ferroelectric material, you have two very fundamental questions to be answered. One, what is the configuration of dipole moment in the ordered region? That means the structure of the domains. Another is when you apply electric field, and then the polarization will switch, and then how the switching process occurs, and in the small scale, like a nanometer scale, even atomic scale. So in the last few years, my research was focused on this, and several students working on this. And we developed two quite important methods. One is using atomic resolution TEM and to determine the spatial distribution of dipole moment. In other words, we can map the polarization in the ferroelectric material from UD cell to UD cell. So what we do is determine position of different kind of cations. This is a bismuth in bismuth fluoride, iron, that is oxygen. So after get all this position, and then you can calculate the dipole moment on this UD cell. Actually, that is very close to the value that in a single crystal. And then with this polarization determined, and then you can map the polarization in the crystal, and then see if there's any deviation from the bulk configuration, and there's a defect, and they may interest in the interaction between the defects or interface. Let's show you one example. So this is a vertical ferroelectric domain. So in this type of domain, the polarization is go this direction. In next domain, the polarization is go other direction. So the rotation is 90 degrees in the plane, but in the three-dimensional space, this rotation is 109 degrees. Okay? So this, you say, from here to here is back to the same polarization state as that one. So technically, this domain wall and that domain wall should be equivalent. Okay? But at the termination point, the characteristic will be different. You can see that this is a schematic show you that a straight termination, there's a defects like here, and then straight termination defects, periodically. So we were first time I see these kind of things, and then would become very interesting. We just focus in this area, so with a two-domain wall termination, and one without defect, another with defect. Then get a high resolution image. And use the method I just explained to map the polarization from UD cell to UD cell. Then you can see that the dipole moment is changing from this direction to that direction by rotation of 90 degrees in the plane. So, and then this domain wall is perfectly fit into the bulk crystal structure. So it's a perfect 109 degree domain wall. And this next domain wall is also 109 degrees. If you compare this part and that part, it's just identical. But close to the termination point, and then the polarization is no longer uniform change, and they have a rotation. We found the ferroelectric vortices and the structure. So these vortices occur periodically every other termination of the domain wall. So this is due to the internal field created by the termination of this dipole, of this polarization. The polarization heads terminate at interface, you have positive charge, and tail terminate here, you have negative charge. From positive to negative, the field, internal field is pointing to that direction. From here is a positive to negative and then pointing in the opposite direction. Therefore, this area, the internal field created by bound charge in this region is favor the polarization change in this direction. But this is not favor the polarization configuration. That's why the polarization have to rotate and then form this kind of vortex structure. This is the method that we developed, and also actually because we see this phenomena and then needed the method to be developed to analyze the polarization configuration. So with that method developed, and then other people also use it to study the interesting phenomena. This is another paper published recently by Shenyang's group, Professor Ma, and he studied the superlattice of lead tartanate, strontium tartanate. And then at the junction between the strontium tartanate and lead tartanate, you see the half vortices of this kind of domain rotation. So these two half vortices are separate quite far away. One is here, another is at the other end of the lead tartanate. So they found this phenomena and then published in the Science. And then about half a year later, and then another group, actually it was also my previous student who developed that method previously. And he joined Ramesh group and then as a postdoc, and then he discovered this interesting phenomena. Basically, that is a continuation of this kind of work. You can imagine if you shrink the size of BTO, and then these two half vortices were getting closer and closer, and they eventually just form a closure domains, right? So this is a perfect, Ramesh doesn't like me to say in this way. So this is an example, right? You see this lead tartanate very small, with a very small thickness. Then this is a STO, and there's STO and BTO. You see beautiful vortices, anti-vortices in superlattice structure. So this is a very nice work and create a new physics in this ferroelectric system. And you can also expect the coupling between ferroelectric and ferromagnetic. If this material is a multiferroic, that means a material which has a simultaneous ferroelectricity and ferromagnetism, you may have the magnetic vortices and ferroelectric vortices coexist at the same time. Then so that you can think about potential applications of this, switching the magnetic state by using electric field. Right? Very interesting. Another very interesting, important question in the ferroelectric material is that how the domains nucleate and what is the dynamic behavior of the domains or the growth of domains, interaction with defects, and so on. In other words, we need to develop a method that can apply bias across a small area of ferroelectric so that I can switch the polarization back and forth. This is the method that we developed. We're using a modified nanofactories holder. We're growing a ferroelectric material with all epitaxial, single crystal epitaxial film. Substrate is a dysprosium scandate, and this conducting bottom electrode is strontium ruthenate. And then the ferroelectric is a PZT, zirconate tartanate. All of them have a perovskite structure with a very good lattice mismatch. Therefore, you grow the thin film multi-halide structure with a very good lattice mismatch. And you can do the electron microscopy imaging, and then you can apply electric field and see how the structure and domain structure change. This is a real, from real data. This is a substrate, this is a bottom electrode, and this is a PZT. And this is a tip, STM tip, is a constant tip. So the tip is pretty sharp, and then apply field between the tip and the bottom electrode. This area is can be switched. You see the switching start from here and then go downwards and then expanding. The field decay quickly from center to the side. Therefore, they only switch in the middle part. Okay? And that is a hysteresis loop, typical for ferroelectric material. You can see that this hysteresis loop is not repeating every time microscopically because the structure is every time is slightly different, right? Depends on the contact. So in this way, you can study the dynamic of the phase transition and all the domain switching. And in the switch region, you can also determine the polarization using the method I explained previously so that it can determine the dipole moment, orientation, and also the atomic scale mechanism. And later, we did a lot of studies and even tracking the change of the polarization just along the moving domain wall if you apply field very slowly so that you can see the unit cell is changing from one state to other state. And this is, I'm not going to talk about the details. So that is for the electrical biasing. So we can use it to study the dynamics of the ferroelectric material. The second example for the application of the modern TEM, especially for in-situ TEM, is a battery study. So I've been working on batteries for a long time, and also in the audience, I've found a lost friend and for many years, and he is really expert of battery, and also the Department of Chemical Engineering and Biomaterials. So many people working on battery material. So I just show a little bit our recent work on this, and so we studied, the nanowire of rutile, and also the nanostructure of the bronze, and to see, because the structure of these two different TiO2 phases is different. This one has color edge sharing on the C-axis and color sharing in the AB plane. Then the lithium diffusion is different from the C-axis versus the AB plane. Right? So another structure is recently become more interesting, the bronze structure, which is not very common process. So, but this structure has a much larger open space, so that people expect this lithium diffusion will be much easier, higher diffusion. So we actually developed a method which is used to synthesize very high quality single crystal bronze B titanium structure without use any water, so that you don't have a water stabilized structure. And then we also studied the TiO2 coated with silicon wire coated with oxide, and then see how this co-shell structure change. I'm not going to talk about all of them. I'll just show you some examples. For those who are interested, we have published many papers in this topic, but then we can talk separately. So what we did is we modify our nanofactories holder, then and change the biasing holder into like solid-state battery testing thermometer. This if you use nanowire, that is very easy to do. So you have a one tip and then have a lithium coated on, put it on top, and usually you have a thin layer of lithium oxide. Put the lithium oxide in contact with the wire. You have another post of copper, and then you can apply field and then see structure and composition change. So Sangju did 3 different material systems. So I'm going to show you one. So lithium insertion in the, I will show you 2. First is very quick. It's a TiO2 rutile structure, and this is a typical nanowire of a TiO2. We apply electric field, and then you will see lithium will diffuse from here, and then gradually change the structure. The structure change have a 2 effect. One is the diameter will expanding, but then the length will shrink. You can see it from here. So initially you have this length, and then shortly and become shorter, but then become much thicker. So Sangju did all this quantitative analysis, and also this change has 2 steps. The first step is a transition of TiO2 from rutile to monoclinic this can be easily determined by electron diffraction. So this is a so-called intermediate state that this lithium will get in, but not fully lithium. So this is a further analysis and what happened during this transition from rotile to monoclinic. You can use electron diffraction. You can also use high resolution image and to confirm this. All right. So if you let lithium diffuse further, and then you get the phase of monoclinic will be changed to another phase. You are rock-celled. Okay? Rock-celled has more lithium inside. But this transition, the previous transition from rotile to monoclinic is reversible. For the monoclinic to the rotile, according to TM study, it's very hard to be reversible because this structure is just changed too much and with a lot of defects introduced. A lot of these planar defects induced due to the big volume change. So this kind of defects is not the way if you try to remove defect seeds. This is a video show all these phenomena, but because I changed the slides, reconfigure my talk this morning, I wasn't able to get video work. Okay? So this is just to summarize. So this the transition during the insertion of lithium in TiO2 rotile nanowire, so there will be two kinds of change: volume change, also phase change. Phase change has two steps. One is from rotile to monoclinic. This is reversible, but intermediate change. And then the second change, phase transition is not reversible. This introduce more defects and also destructive. Sanju just finished, but he's now back to Korea and do military service. The second quick example is bronze phase. The bronze phase, before we study, there's like the single crystal bronze phase in thin film form. And all the thin bronze phase was studied for as an anode with the nanostructures, especially the Bruce group. Very nice nanostructure. But all these methods involve water. And many people suspect the property is with water molecule stabilization. So we use a post-laser deposition and to make the bronze phase a very nice epitaxial film, almost perfect. And we discovered this by as a side product of a catalyst study. We studied a so-called intelligent catalyst. Is a platinum or palladium doped calcium tartanate. And during the reaction in the hydrogen, and then we see this kind of small secondary phase of titanium bronze B. And then we figured out there is a structural relationship between this secondary phase and the perfect perovskite. And then we use this as a template and to grow epitaxial film. It was become very good, very successful. So then we make a very nice bronze phase of TiO2. I can even use a calcium-doped TiO2 bronze structure. And so we have two different kind of model structure. By changing the substrate orientation, we can also grow the bronze B with different phases. That means the diffusion channel can be in parallel to the film or perpendicular to the film. Then we just do the thin film battery testing, and then you have different channel of diffusion. This was the work of Kui Zhang, and he published bronze material. He also just graduated last year. So then, this is the typical nanostructures from the Bruce group. And then this is a thin film, epitaxial thin film from my group, and Kui Zhang, and did this work initially, and then and Sangju and studied more about microscopy side and also the In-situ TM. So all the battery study was on the thin films, with very thin films. And he found that the titanium B is better than calcium bronze B. And also with a calcium bronze B, you can grow the channel in plane or out of plane. Okay? And then you see that out of plane channels will provide much higher capacity than those in panel. So this is this kind of structure. Then that one, green one, is structure like this. Okay? That means diffusion channel is limited by the epitaxial growth. This is Sangju's in-situ TM work on this epitaxial titanium B. We use niobium-doped STO as a bottom electrode, by field across this lithium and niobium-doped STO. And I want to show you some defects that is seen in this. Doesn't allow me. I think I just didn't get this file very well. So you can see that by apply electric field between lithium and the conducting STO, and then it would introduce a lot of planar defects. And this planar defect, you can see they continue to grow, right? So you see this was not here. This was already there when we were recording images. That occurred quite quickly. Then you can see more and more this kind of linear, actually I call linear is actually in 3D, this is just a planar defect. We see a lot of these planar defects are nucleate. Those planar defects tend to be anatase phase insert gradually into the bronze B structure. We have a more and more lithium and diffuse into this structure. You see more and more defects. That looks like anatase phase become more stable during this transition. So this is all the details that Sangju study, and they can see more, and also the anatase thicker and not very thick. I hoped, when I see that, thin layer of anatase, and then say, okay, if you continue to insert lithium, can you just make this transition from bronze B to anatase and vice versa? And he tried and couldn't do it. It's just a limited amount of the planar defects, with a anatase. But he will see more shear planes. We have a lithium insert, and then the volume is changing, and then the volume change generates strain. And the strain relaxation, one of the mechanisms is shear plane. Generate a lot of shear planes in the structure. Okay? So, and there's some area, even with the structure, which is completely different from the bronze structure. So this is one of the that he analyzed. And this area of this phase, lithium is really high in that area. I want to summarize for this lithium and diffusion in different kind of TL2 structure. So in the TL2 nanostructure, we see two steps of phase transition, from rotile to monoclinic, and then from monoclinic to oxale. First phase transition is reversible, and second one is not. And then for the bronze B structure, so we have two kinds of bronze B, and calcium doped, and also pure TL2. Pure TL2 has a little bit higher capacity than bronze B. But bronze B, we can make two different kind of texture. One with diffusion channel in plane, another is out of plane, so that we can test the difference between difference in the lithium diffusion on different channels. And also with the in-situ TM, we see there's two kind of defects formed during the lithium insertion. One is the very thin layer of anatase formed in the bronze B. Another is due to the strain relaxation, a lot of shear plane formed in the bronze B structure. Right. So the next So I will talk about the topic that I initially planned to do. Okay. Is on catalyst. So on the catalyst, I've been studying catalyst as soon as I moved to Michigan. for about 20 years. I have a close collaboration with a Ford Motor Company, and many working on the automotive catalyst. One of the very interesting problems they draw my attention was the aging effect. The catalyst, due to operation and then gradually age. Encapsulation. So precious metals gradually encapsulated by the oxide support. And then later, after we got a lot of experiments done, and then they are happy. Then I ask, can we do the reaction in the real time? Can you see, what happened in the real time with high pressure? And I said, this is a very good question. And then, we try to develop method to do this. And I work with Larry Elliott at Oak Ridge National Lab, and two of my students was with him 8 years, and in collaboration with Protochips company. They developed different kind of version of the gas reaction holder. Only until 2 years ago, they successfully developed this kind of atmosphere pressure holder, and that really can do experiment in the high pressure, and then we get some data. So most of this work, although it is published, and it's just quite preliminary, we are still working on this area. Basically, you can do the high pressure in-situ experiment in TM with two different ways. One is you so-called environmental TM called ETEM. ETEM is from FEI company. They have built a special pole piece so that around pole piece the pressure is differentially pumped, and then you have a high pressure in that area. Introduce a different kind of gas, and you can see visual microscopy and spectroscopy. But this pressure is still pretty high, and they could do probably 50 torr or 50 millitorr dot. You see. ETEM is until about 10 millibar. Okay, so the simple reason is that if you increase pressure further, and then the diffusion pumping will not be efficient, then the microscope will not work. Another way is we do not use the special built galvanometer. We just use a regular TM, but build a holder which has a two-piece of membrane so that the gas can go in and pump out, and then in the real time, just through very small volume, okay, between two membranes. So this is the method that Protochips developed. I think they told me a few days ago. I should convince you it is safe to use. Okay. So we got the beta test and 2 years ago, then working on this autocatalyst, the automotive catalyst. And then this one allow you to do experiment to atmosphere pressure, truly atmosphere pressure. So this is a holder, and this is the control system for the gas, and then everything is optimized with hardware, software. There's a bit details about the structure of this product. You have a two E-chip and for heating, and then have a membrane, and so that the gas is limited in this very small volume. So this is just an exaggerated volume of gas. So there's a lower silicon nitride membrane, up silicon nitride membrane, and then there's also E-chip. You can heat the sample to 1,000 degrees C. And then you can see, how this gas interacts with a small particle of catalyst, which is put on the top of the top part of the membrane. Actually, during the experiment, you can either put it here or here, depends on which EM mode, which mode you use for imaging. If you do STEM mode, you put it here. If you do TM mode, you put it here. Okay. I'll just show you some data. I'm just going to ignore the introduction part, most introduction part. This first example I want to show you is the catalyst that developed by Gorty at UPenn. And he has, is interested in the catalyst and for the immersion combustion. And then for the typical catalyst for this purpose, and that is only working at a high temperature. Later on, when people develop this so-called, the nano-sized, oxide and its support, and just mixture of two different nanoparticles, metal and oxide. And then the efficiency is, at the intermediate temperature, the efficiency is also enhanced. But then he developed this so-called, he called cold shell catalyst. Have a platinum core. All right, so it's a platinum core, and then surrounded by serial oxide particle that he called shell. And this kind of a cold shell structure, he thinks is critical for this kind of improved catalytic activity. And his catalyst can have a very high activity at even 200 degrees C. That is significantly lower than the traditional catalyst. Then you see he did this work and realized, and he published in Science about 3 or 4 years ago. And then he said, oh, now you have this gas cell, and can you just put it in and then do the same treatment as he did for the in-situ test and see if this cold shell structure. He just wanted to see how this cold shell structure looks like. But in the end, we could not, he doesn't have this predicted cold shell structure. Basically, just a mixture of two kind of particles, metal particle and oxide particle. But after reaction, then there will be very interesting structure stabilized, and that is enhanced activity. So that's basically just one thing. I can tell you more about using this sample and then see a lot of interesting phenomena that was interesting for people like ceramists or metallurgists or the chemists, because the atoms were leaving the particles at high pressure, high temperature, and high atmosphere pressure. And then you see the atom clot and moving around, and then the small particle disappear, large particle growth, like typical sintering effect or the Oswald ripening, and a lot of things. I'll show you a few examples. So this is the in-situ experiment, and showed how his catalyst looks like. We do not see the summarized to this. The finding of this is just we do not see the cold shell structure. In the in-situ experiment with atmosphere pressure gas holder, then we put this catalyst inside, and then with oxygen, 20% oxygen, nitrogen, and then heat it to 500 degrees C, and with 150 torr pressure. Then you can see that this sintering, you see the small particles just disappear, and then some particles just merge with each other, and then some particles become bigger. This is small examples in the same experiment. Okay? But the important, surprising finding is that there's a lot of small atomic clusters forming during this process. If you reverse replace high oxygen to hydrogen, and then this will disappear, and gradually the particle will go further. You can do this back and forth. We call redox reaction. So this is two particles, actually three particles, 1, 2, 3, and then gradually you can see that these two will just merge, and then leaving some kind of atomic cloud here. Then this one are much smaller than the initial. Small example, you can see the particle rotation and so on, and you can do, if you are interested in how the transformation, transition between two particles to one particle, and then the surface energy, like a crystallographer, they study different kind of special grain boundaries, and the particle will rotate and then have a very nice match at the boundary, and then suddenly the particles will just merge, become one. And this process is too fast to be seen by STEM. The scanning mode is very slow. Now we have a direct electron detector, K2 IAS camera, recording 1,500 images per second. With that camera, we are intend to study the details of dynamic behavior of this kind of structure change. I want to just quickly move to another one, example of fuel cell catalyst. So this is a interesting catalyst for the fuel cell application. Platinum cobalt alloy. Platinum is very expensive, and then cobalt is much cheaper. So if you can replace at least partial platinum, and then will reduce the cost. And also this recent study showed that cobalt alloy on this particle has an even higher activity. So you see this with 25% of cobalt, then this alloy catalyst have a much higher activity for the fuel cells. This is just a few studies being published, especially with using atmosphere and see the structure change, order, disorder, and so on. And we try to study this material with disordered platinum cobalt. And then first see how this disorder to order transition. And then after the transform into the ordered phase, then in the oxygen and hydrogen atmosphere, and all the structure change. This was the purpose of our study. We, by X-ray diffraction with in-situ experiment, we see that our material started with is disordered. It is a no 100 or 110 peak. This means that the structure is disordered. Okay? So this is in TM. You can see that this is confirm this is the disordered. And if you put in the TM with 1 atmosphere oxygen pressure, then heat it to 700 to 750 degrees for 30 seconds, you can see that the structure transforms to perfect ordered. Okay? If you do Fourier transformation of this image, you can see that the 100 and 110 So we can easily transform to the ordered phase. After the particle become ordered, then you just keep the temperatures at the same temperature. You do not see anything strange, except you have 2 layers of platinum instead of just 1 layer. You have a platinum, cobalt, platinum, cobalt, platinum, platinum. Okay? But if you lower the temperature, after particle is ordered at 750, you do not change the atmosphere. Just lower the temperature to 300 degrees C. Then you can gradually see the formation of more platinum shell on this ordered particle. This you see initially we see 2 layers already. Then after 64 seconds, 1 minute later, you can see that this layer becomes 3, right? 3 platinum layer. Then another minute, then you can see a 4 layer on the surface. You can see this is edge, okay? Also, this is contact with another particles. But you can see here, 4 layer, but not other area. Only 100 phase will form this platinum multiple layer, not on the other surface. That means it depends on surface allergy. This is a summary of the few steps. So 1 minute later, 3 layer, another minute, and 4 layer. And then we see 6 layer as maximum. I think this is limited by the source of platinum in the system. All right, so we see this. The first step is order-disorder transition that happened at 750 degrees C in the oxygen atmosphere. Then if you lower to the high to 300 degrees C with the same atmosphere, and then you see additional platinum shell form on the 100 phase, not on other surfaces. So in the final product we see during this treatment is we call it core shell structure. Ordered platinum cobalt core and with a pure platinum shell. Right, when we got to this experiment, and we talked to Professor Ru Chen in physics, he's a theoretical scientist and expertise, first principle thermodynamic calculation for different material. He worked with good enough and for many years, so he knows this system very well. And this calculate surface energy with different kind of composition, different kind of atmosphere condition. And it turns out this 100 phase has lowest surface energy in the oxygen atmosphere. The other phases, energy is significantly higher. But only platinum 100 has a low surface energy, so that can form to cover this platinum cobalt particle, stabilize it, oxygen atmosphere. I think that was what I want to say about catalysts. So we can have the experiment done with high atmosphere pressure, still remain atomic resolution. And with the TM mode, and plus G10 direct electron detector, so-called K2IS camera, we expect to do more experiment to see dynamic change, and which happen much faster than we can do with STEM. So that was my talk, just too many different topics. I hope give you some idea about the advanced TM, and like Professor Wang set up here, and I think many people I know, and I have visited many universities in Hong Kong, and they are looking forward and to use this exciting instrument. We have many different kind of holder as well.
Right, thank you.
Very much.
Yeah, okay, thank you, Professor Pan, for exciting talk discovered by electron microscopy technique and atomic scale. Now, question.
Very exciting and so many techniques that I brightening. I have probably a silly question which I couldn't catch. For the normal X-ray diffractions, I think FCC, and the 100 peak doesn't show up, right?
Yeah, that's a disordered.
Yeah, but in your case, the 100 diffraction, I see when you show the diffraction, 100 comes up. So what is the case? Why that is the case? Probably you don't have too many layers. It doesn't give you the line distinction?
No. So here, you do not see 100 and 110 because this is initial disordered. After you put TM and heat it to the high temperature in oxygen atmosphere, and then you form this ordered phase. You can see that this is too thick. You can distinguish platinum and the cobalt, but in the thin region you do. But they do first Fourier transformation. You see that 100 and 110 occur. That means the phase is ordered.
I see. I didn't.
So the way to distinguish disorder and ordered phase, the occurrence of 100 or 110. This is the ordering occur.
Oh, it is.
Thank you very much. I have a question about the first example for the atmospheric EM. And so you saw this atomic cloud. You emphasized this a few times. And I assume that the atomic cloud is something that you can only see when you're near atmosphere, right?
Yes.
What do you think? What is this an atomic cloud? I don't understand what the structure is of this atomic cloud.
We don't know. And I give one slide to compare E10 with a high atmosphere pressure holder, right? So E10, the advantage is that you can have a spectrometer, mass spectrometer built in the system. But here, in our current version of this gas cell, we even do not have EDS. But they do now. And so they are upgrading next month our facility. And EOS, technically, you can do EOS, electron energy loss spectroscopy, so that you can determine chemical but the membrane is too thick. Multiple scattering is still a problem. So EDS will be a good way.
What are your hunches? What are your best guesses of what this atomic cloud is? That
I guess it's just, this, I guess, Ferric oxide should be stable because this is oxygen atmosphere. Platinum will be volatile. So they just, because a platinum particle just probably just dispersed. And before they react or from other kind of phases, just floating around. This is what I mean.
very mobile,
Yes.
very moving around. So
Yes. You can see that
Yeah,
actually
yeah.
each time is not staying in the same area.
okay, so the integration time is too long to capture
Yes.
there. Okay.
It'll be great. So there's another part with the in-situ IAS camera, and that will be.
Hopefully 1,500 frames is enough.
Yeah, it could be much faster than the camera.
Thank you very much. This is very powerful and interesting technique. Definitely.
Oh.
I have actually a suggestion. You've shown that you mastered the probing, in-situ probing of electrochemical in-situ probing of berries. You also showed that you can study the activity of catalysts using oxygen atmosphere
Right.
and temperature. I was wondering if it's feasible to combine both. The reason I'm saying that because a lot of activity now in lithium oxygen, and you have a catalyst, and very few people understand how the discharge product is catalyst. An example, we recently published a paper where we were able to stabilize the superoxide, say that is oceanate easy. And we find out, we use iridium catalyst, found out actually the catalyst change. Maybe some matching, structural mismatch, catalyst and the crystalline superoxide that we found. But that was a determination based on modeling of team calculation. It would be really interesting, and I'll be very happy to collaborate with you on this one. Build a probing device that can allow you to do electrochemical probing
And in the atmosphere.
in an oxygen atmosphere.
Yeah.
So is it feasible? That's my
I think it's possible, and just you change the E cell, and you can, in addition to heating, you can also use that to do biasing. I think that would be a combination of electrochemical holder and gas holder. Yeah, so I think it's worth to approach.
What is the lower limit you anticipate your technique further development?
Oh, no limit, because we want to see. This so far is not as good as expected, right? You want the atomic resolution, sub-angstrom resolution, also the chemical analysis, and chemical analysis may can be done, but people will be interested in other properties like magnetic, vibrational. For those working on chemical stuff, right? You want to see the molecule vibration and so on. And this is another thing I did not talk at all. I think last time I mentioned in one slide. So one of the microscopes I show you here, the very first one, called Neon dedicated stem. That is the most expensive one. That microscope has a very high spatial resolution, higher than any other microscope, 0.45 angstrom. But the most exciting part is for that microscope is the high energy resolution. Energy resolution can be guaranteed for my microscope is 7 millieV, and then it will be 5 according to the developer, because our room is very, very, really, really good. So with less than 10 millieV, you can study the vibration of molecule. The developer is Andrea Kremenek. He published the pioneer work 2 years ago, Nature. So special result, vibrational microscopy, showing that hydrogen in the silicon nitride or some other things is clearly distinguished vibration mode of the light element. A higher energy resolution, you can vibration mode of many elements. So this is in-situ TM, just as I said, no limit, just was different technique. This is so many things you can think, which is still not possible right now. But in the future, there's many tools developed. When I was a student, Professor Wang and I, graduate school at the same time, we started in a TM, just a tool is very well developed and used for imaging, and that's it. And then 10 years, 15 years later, then the operating corrector become routinely available. That pushing the microscopy to another level. Now, there's so many in-situ tools being developed. Now, energy resolution is also further improved by state-of-art monochronometer. There's a lot of things to do in a decade for microscopy.
When you talk about this energy resolution, you talk about instead in vacuum, right? How about in the gas cell and the liquid cell?
Actually, that's why I'm saying no limit, right? People always ask a question, can you do this? A more challenging question. That is very, very exciting. So the microscope I ordered is called Lion Delegate STEM, called Ultra STEM, right? That is have a very high energy resolution, spectral resolution. And I have an option in the future, if the site entry version is stable, and I will buy that part. So there is a win and the development. The Lion company collaborate with a laboratory in Auxerre, France. So they are developing site and changing the galvanometer and a site entry holder, so that you can just have sample holder developed, insert, and also with a coating stage. And the first step is liquid nitrogen. We all want to, can we use a liquid helium? So that if that is developed in a few years, you can do high energy resolution of vibrational microscopy in different atmosphere. Okay? It's possible. It's waiting for, this is a small company. All these tools have to develop gradually.
In the gas and the liquid, the electron has a lot of scattering, right? What's the problem, right?
But you have to limit the volume, right? Exactly like a gas holder. Gas reaction holder, you have to, the membrane, two pieces of membrane have to be very, very close to each other, so that electrons only suffer a little bit multiple scattering between the two membranes, not the rest of the column. This is also the reason why the E10 do not have a much higher pressure as the gas cell, because E10, the Popey's region is a larger volume with a high pressure. That means you can only use a slightly lower pressure so that the mean-free path still work for that.
So another question for this, already the question about the atomic clouds is actually that really the active catalyst.
We don't know. Like I said,
core shell is not all. It's already destroyed, right? No core shell anymore. So the actual active catalyst is not a really core shell structure. Is that right?
Right. So no. I have to distinguish between what I see here and what Gordy proposed in his science paper. So here we do more experiment, more aggressive reaction than what he did in the bigger test. So in our test, at that stage, and most metal, platinum, I think is already. That's why we see so many clouds. But I cannot make statement that gold is a catalyst during operation. That kind of, we cannot go that far. He's co-author on my paper.
Let's thank Professor Pan again and end the seminar. Thank you for expand.